So, in our last lecture, if you recall, we looked at various ways of increasing the instruction level parallelism in a program. Okay. So, we looked at the very well known technique called loop unrolling, which is used by compilers to expose more parallelism in a program, and also it will enable the compiler to do instruction scheduling, move instructions around to reduce the number of stall cycles. So, we also saw the so called superscalar and VLAW architectures, which can enhance the performance of a pipelining by allowing more than one instructions to be issued in every clock cycle. So, in this lecture, let us look one step further. Let us see how we can further parallelize computations, but we are looking at specific kinds of computations that are carried out on something called vectors. Okay. So, the topic of today's lecture is vector processors. Okay. Let us try to see first that how we can look at the constraints in a pipeline and what are the factors that limit its performance. Broadly, there are two factors. The first factor relates to the clock cycle time. Like you see, in a pipeline, if you can make the clock cycle time faster, then obviously your instruction execution will become faster. So, your instructions will execute faster, you can issue instructions at a faster rate, and this clock cycle time can be reduced obviously by making the pipeline stages simpler, which means increasing the number of stages. But if you increase the number of stages, there will be one difficulty. You see, here earlier in the Mips32 pipeline, even though there are 5 stages only, you saw that there were a lot of dependencies and hazard creating scenarios that were coming. So, by using forwarding and other techniques, we could reduce most of them, but still for certain dependencies we had to use some stall cycles, right. So, if you increase the number of stages even further, this constraint will become even more pronounced. There will be more kinds of dependencies that will be showing up. Okay. So, this clock cycle time reduction by increasing the pipeline stages can increase dependencies in general, which can result in a higher cycle per instruction or CPI. The second constraint is the instruction fetch and decode rate. Okay. So, here what you are saying is that the instructions have to be ultimately fetched from memory, right. So, earlier we were saying that one instruction has to be fetched per cycle, but now when we are moving into superscalar and other kind of parallel kind of computation, here we are demanding that in every clock cycle we need to fetch more than one instructions. Well, of course, this has something to do with the way we are organizing our memory. You have studied earlier that if we use memory interleaving, we can have some kind of parallel access. For instance, for a 4-way memory interleaving, we can access or read 4 words in every clock cycle. Organization of the memory also produces a constraint to the maximum memory CPU bandwidth. Okay. Now, this processor memory speed gap is sometimes also referred to as Flynn bottleneck. Okay. So, in general, as I said, there is a limit to the number of instructions that can be fetched in every clock cycle. So, now we are moving on to vector processors. Let us see what a vector processor is. Well, here we are operating on entire arrays of numbers called vectors. Like, let us say I have an array of numbers, not one, but several. Let us say there are a total of 64 numbers. So, what I am saying is that all these 64 numbers taken together we are referring this as a vector. So, what we are saying is that let us say A is a vector, B is also a vector, A, B are vectors. Let us say C is also a vector. So, where I want to store the result. So, I can simply write an instruction, well, logically I am writing like C equal to A plus B. This is an example of a vector instruction where although we are using a single instruction, but actually 64 additions are taking place. The first element of A is added to the first element of B, second element of A is added to the second element of B, and so on, and the results are stored in the corresponding elements of the vector C. Okay. So, in a conventional processor where this kind of vector operations are not there, we had to use a loop. In every loop, in every iteration, you have to add one pair of numbers, then decrement a loop counter, check for 0 or some condition, then again branch back. So, there you see some loop overheads were there, decrementing a counter, branching, but here it is a single instruction, there are no loop overheads. So, expectedly this should run faster. Okay. So, as I said, a single vector instruction is equivalent to an entire loop, and as I said, no loop overheads are required. Just the example that I have given, that we are adding two vectors, let us say the instruction will look like this: add vector v1, v2, v3. So, v2 and v3 are added element by element, the result will be stored in v1. So, this single instruction can compute a set of additions like Ci equal to Ai plus Bi, where I will vary across the length of the vectors, right. So, each of these elements can be, for example, double precision number 64 bits, right. So, if you can map the vectors to the so called vector registers, we can use a single instruction to add them. So, let us now look at the basic vector processor architecture. How does it look like? Well, just inside a vector processor, the basic hardware is nothing but a heavily pipelined scalar unit. You see, vector processor is an extension of a pipelined processing unit, you can say. It is like a normal pipelined instruction set architecture implementation, where in the execution unit we earlier talked about multi-cycle operations, right, where the execution unit, the arithmetic units were also pipelined. Here the arithmetic units are separately pipelined, they can be separately fed with data, the results can be picked up separately. So, means it is an extension of that multi-cycle kind of a concept, you can say. So, all the functional units will be pipelined, deeply pipelined to the extent possible, so that you can feed data at a faster rate. Okay. So, there will be two things, one will be an ordinary pipeline scalar unit, and in addition there will be a vector unit. Vector unit will consist of the vector registers, the arithmetic units, and so on. So, as I had said, so inside the vector unit, all the functional units like adder, multiplier, divider, etc., they are all deeply pipelined, so that for execution in the functional units, the pipelined clock cycle time will be as less as possible. Now, another thing you see here, in a normal instruction set pipelining, when we are feeding a number of instructions sequentially in the pipe, there were the situations of hazards. But for vector operations, suppose I am adding two vectors A and B, storing the result in C, there are 64 operations which are going on in parallel in overlap fashion, let us say, but these operations are all independent, like A1 and B1 are added, result is stored in C1, then A2 and B2 are added, result is stored in C2, and so on. There is no dependency across successive computations. So, no question of hazards coming in. This is another very good thing for vector processing. Okay. So, this kind of deep pipelining do not result in hazards because the computations are independent. So, let us look at a hypothetical vector processor which is an extension of the Mips32 architecture, you can say. Let us look at it. This is a very high level schematic I am showing you. Let us say there are 8 vector registers V0 to V7. Let us assume each of these vector registers can hold 64 double precision numbers. So, each of the registers is actually a set of 64 bit registers. Okay. So, there are 8 such, and these vector registers, 2 of them can be read and you can write into one of them every cycle. So as you can see, this input and output links, and in addition there are the standard scalar registers as you saw in Mips32, the integer and the floating point registers. There is a memory system. The memory will be interfaced to the scalar register just like as you saw earlier, but in addition there will also be a vector load store unit through which you can load an entire vector from memory into one of these registers, or you can store one of the vector registers into memory. Okay. And on this side you have the vector functional units. So, you see there are so many vector function units, each of them are having 2 inputs and 1 output, and they can be fed concurrently. So, the bandwidth of this bus should be high enough so that while some vector addition is going on, in parallel a vector multiply should also be go on. So, it really does not mean that these arrows will mean that 1 and 2 data are coming together, not 2, it may be more than 2. So, in general all of these functional units, if there are 5, there will be 10 such numbers that can come in every clock, and similarly 5 of the results can be stored in the registers in every clock, right. This is the basic idea, and all of these units are heavily pipelined. Now, as I said, in that architecture there are 8 vector registers. So, each vector register, as I had mentioned, can hold 64 numbers, each are double precision or double words. Each vector register has 2 read ports and 1 write port, as this diagram shows. Each vector register will be having 2 read ports and 1 write port. So, it is not just for the whole bank, but for each of the vectors. Okay. And for the vector functional units, they are all fully pipelined. They can start a operation every clock cycle, and if there is any dependency means across these functional units, like I am carrying out a vector addition, the next instruction is a vector multiplication which uses one of the vectors that is produced as a result. So, there will be a latency or a stall, you have to wait. Okay. This is kind of dependency between instructions, but within an instruction there are no dependencies. So, all the 64 operations can go on in an overlapped way without any stalls, without any loop overheads also. Okay. Fine. So, if there are any dependencies across instructions, then stall cycles can be inserted. So, regarding the vector load store unit, as I said, that is also fully pipelined, and it allows fast loading and storing of the vectors, and to allow this the memory system has to be very deeply interleaved. So, 2-way or 4-way interleaving will not do, maybe it will be 16-way or 32-way or 64-way interleaved. So, memory organization has to be much more complex. If we have to read a vector whole 64 words or double words in one cycle or in a very few number of cycles, right. So, you need to modify the memory system as well. So, after the initial latency which can indicate the access time of the memory, you can access the words 1 per cycle. And in addition to that, the scalar registers are also there, like Mips32. These are the normal integer and floating point registers. Now, these registers can be used to carry out integer operations, of course, but they can also be used to provide data as input to the vector functional units. There are some operations where you may want to add say a scalar number to all the elements of a vector, then the scalar number can come from one of the vector means one of the scalar registers. Okay. Moreover, you can also use the scalar registers to compute the memory address which will be used by the vector load store unit, from which memory address you want to load or store. Okay. So, scalar and vector registers can be used together. Let us take an example. So, we look at a computation like this, y equal to a multiplied by x plus y, where this x and y are vectors, a is a scalar. Okay. This is sometimes called single precision Saxby or double precision Daxby loop. Saxby stands for a x plus y, a x plus y. So, if it is in single precision, we call it a Saxby loop. If it is double precision, you call it a Daxby loop. Here we are assuming that x and y are both vectors of size 64 and a is a scalar. Well, for convenience, for ease of our programming, let us assume R x is a register that contains the starting address of the vector x in memory, R y is a register containing the address of y, and the scalar register R 1, it contains the address of the scalar number a. So, the conventional Mips32 code to add these numbers will look like this. So, what we do? We load the scalar number a, this R 1 contains the address, into F 0. This R x contains the starting address of x. There are total 64 numbers, double precision. So, there will be 512 bytes, because each number will be 8 bytes long. So, we are adding 512 to R x and storing it in R 4. So, R 4 will be storing the memory location which is immediately after this vector x. Vector x is there, R x points to the first element and R 4 will point to the element just after the last element. So, we will be incrementing R x and we will be comparing whether it is becoming equal to R x, become equal to R 4, and when it becomes equal we will stop. The idea is like this. Then we come into the main loop. We load the first number R x, multiply it with the scalar is in F 0, F 0 and F 2, result is stored back into F 2 into R x. Then we from there we have to add y. Okay. So, we load the first element of y, store it in F 4, this F 2 we add to F 4, store the result back in F 4 and we store it back into y, because result have to store back in y. Okay. Store it y. Then we increment x pointer by 8, point to the next number, y pointer by 8, then check whether this R 4 and R x are becoming equal. If it is not equal, you jump back. This is Mips32 code. The equivalent vector computing code will look like this. Here we are loading the scalar number into F 0 as usual. This is a load vector instruction. Load vector V 1 0 R x will load the entire 64 element vector into V 1. Then we are saying multiply scalar with vector, this is an instruction mult sv. We are saying multiply the scalar F 0 with all the elements of the vector V 1 and store the result in V 2. Then we are loading the vector y into another register V 3, the whole vector. Then you are adding V 2 and V 3, storing the result in V 4 and we are storing the vector finally back into R O y. Right. Now, you see in this code there are no loops. Here these three instructions were the loop overheads, this add immediate and BNE. Here there are no such. This is the big advantage, okay, vector process. There are only 6 instructions here and here there are 3, 4, 5, 6, 7, 8, 9, 10. So, the vector processor, one advantage is that it reduces the dynamic instruction bandwidth. What is meant by dynamic instruction bandwidth? It is equal to the number of instructions that are actually getting executed. Let us look at the Mips32 code version. Here the loop was this 1, 2, 3, 4, 5, 6, 7, 8. There are 8 instructions in the loop and the loop was going 64 times. So, 8 multiplied by 64 is how much? 512, and outside the loop there are 2 more instructions 514, but here there are only 6. So, earlier 514 instructions were fetched and executed, now only 6 instructions will be fetched and executed. Okay. This is a great reduction in the instruction bandwidth. Similarly, the stalls, the pipeline interlocks are also greatly reduced, because in the original Mips32 version you will see there will be lot of dependencies, like going back again, you see this add uses R4 which is loaded here, there is a dependency. Similarly, this add generates R4 which is stored here, there is a dependency. Like this there will be several, like here this F2 is loaded, next instruction you are using F2, there are lot of dependencies. But here within the vector instructions there are no dependencies, but across there can be, like here you are loading V1, next instruction V1 is used, like that. Okay. So, the vector processing instruction, the stalls are required once per vector operation, that means instruction, rather than once per vector element. In the original version, stalls are occurring in every iteration, that means once per vector element. Here within a vector instruction there are no stalls, but between vector instructions there can be stalls. Okay. So, in general the pipeline stall frequency is also reduced by almost 64 times. These are the main advantages. Now, there is something called vector startup and initiation rate. You see, the running time for the vector operations has 2 components, one is called the startup time. Startup time means after how much time the first result will be available. This depends on the depth of the pipeline. Because of the pipeline latency, this is determined by the depth of the pipeline. So, if I say that my startup time is 8, this will mean that my pipeline depth is 8 and it will take 8 clock cycles for the first result to come out. Okay. This is my startup time. And initiation rate is that once the vectors are being operated on, what is the delay with which I can feed the successive elements of the vectors. So, it is usually 1 per clock cycle, because the execution units are deeply pipelined. So, in general, if you have a vector operation that is operating on n elements, typically n is less than or equal to 64, then it will be equal to the startup time, the time taken for the first element to become available, plus number of elements multiplied by initiation rate. As I said, initiation rate is typically 1. So, it will be startup time plus n roughly. This will be the total time to compute the operation. Let us take a simple example. Let us say the startup time of a multiply operation is 12 clock cycle, which means it is a 12 stage pipeline. So, after starting up, initiation rate is 1 per clock cycle. So, we are trying to estimate what will be the number of clock cycles required per result for a 64 element vector. You see, for all the 64 element we can use the previous formula to compute the total time, startup time plus n multiplied by initiation rate. Now, I want time per element per result. So, we are computing 64 results, divide by 64. So, it is 1.19. So, in 1.19 cycles we are getting one result, okay, for the vector operation. Now, there are certain factors which affect the startup time and initiation rates. Like for register to register operations, the startup time, this I have mentioned already, will be equal to the number of stages in the pipeline. depth, and initiation rate typically 1. This is determined by how often you can feed a new set of data to the pipeline, to the function unit. Now, typical depths are as follows. For floating point operations, this addition subtraction typically requires 6 stages, taking into account the Mantis alignment, normalization, everything, and floating point multiply require 7 stages. But if there is any dependency between vector operation, that means if a computation depends on an uncompleted computation due to a previous instruction, then some stall cycles may need to be inserted, typically extra 4 cycles. These are some very typical values, this can vary of course. So, let us take an example like this, where the operands are all independent. This operation V2, V3 stores in V1, this V2, V4 stores in V5. So, there is no dependency. For such cases, so you can proceed without any penalty or delay, but if there is a dependency, then in the previous slide I mentioned some extra cycle startup penalty is there, that penalty have to be given for the second instruction. Even with forwarding, you have to wait for this operation to be complete, then you can forward it here. Okay? Fine. So, sustain rate is defined as across a number of operations, what is the time per element for a collection of operations. Let us take an example. Let us say there are 2 instructions like this, multiply followed by add, and the operands are of length 64. For the multiply instruction, the starting time is 0, because in the clock cycle 0 it is starting. So, completion time will be 7 will be the startup time for multiplication, plus 64 into 1, 71, and add will start after 1 clock cycle in a pipeline. So, its starting time will be 1. So, completion time will be 1 plus startup time plus initiation time into 1, 71. So, in total 71 clock cycles, we are completing 64 plus 64 128 operations, floating point operations. So, 128 floating point operation in 71 cycle means 1.8 flops per cycle. This is the sustained rate. Fine. Talking about the overheads of load store unit, we just mentioned it earlier. Well, you have the CPU, you have the memory here. So, here the memory has to be very heavily interleaved. So, you can access these banks in parallel, you can store them temporarily in registers, and through a multiplexer demultiplexer network, these registers can be read or written at a very fast rate to the CPU or from the CPU. So, for load operation, the startup time will be the time to get the first word from memory into register, that means it will be equal to the access time of the memory. So, how much time is required to get the data here and the multiplexer to forward the first data. And since the remaining data are already in register, you can feed them one by one at successive clock pulses. Okay. So, vector initiation rate will be equal to the rate at which new words can be fetched. So, this memory organization has to be done very carefully, such that very high data transfer rate can be sustained. For stored operation, here startup time is not that important, because store does not produce results in some vector register, it is storing into memory. But if there is a load instruction followed which follows the store and it uses the same data, then the load may have to wait. These are the typical startup penalties. For add, multiply I have already said 6 and 7, divide it is typically 20, and for load and store also it is typically 12. So, just there are other vector processing concepts I am very briefly mentioning. Well, sometimes you may have a situation where you do not have to operate on the whole 64 element vector, maybe you have a vector of size 30. Then there is a register called vector length register, you can load it with 30. So, only the first 30 elements will be operated on. Okay. So, vector length register. Second one is loading and storing vectors with strides. This is something like this. See, normally when you are loading a vector from memory, you can say that I will be loading them from consecutive memory locations, that is one way. Other thing is that you can specify something called a stride or a gap. Let us say the gap is 10. So, the first vector element is loaded from say memory location 0, the second is loaded from 10, third is loaded from 20, 30, 40, that means at a gap of 10. This is sometimes used, say for example, if you have a 2-dimensional array, they are typically stored in memory in row measure or column measure order. Suppose you want to load a row or a column of the vector in a register. If you use stride, you can do both. For column, if it is stored in row measure order, if we have a gap, you can access the elements in a column. By specifying the stride, you can also load the column in a vector register. Okay. So, this is, and third is called strip mining. Strip mining says that, well, your vector register is of length 64, but suppose my original program that I am running, it means it is running for let us say 200 cycles. So, what do I do? So, 64, 64, 64, I can do it for 3 times. So, it will be 192. So, I will be 8 vector elements will be left. So, this is called strip mining. So, I will be factoring it out 64, 64, 64, and whatever is left out, that I will be using as a separate 4th vector operation. Okay. So, these are some concepts which are there along with vector processing, which helps a programmer to write vector programs. So, with this we come to the end of this lecture. So, I just tried to give you a brief overview about what vector processing is and how vector computers work. So, I mean, if you look at a real vector processor that is available commercially, you will see that there are a lot of other details and other nitty-gritties involved there, but here we are not going into that details. Thank you.